In this video, we're going to go through the first question of IChO 2026, which is a question that has a lot to do with symmetry. So without further ado, let us begin. If you haven't tried the question yet, at this point, please pause the video and try the question because it's really good exercise, and I think this is a quite a well set question, so it's very worth trying. Okay, so this question begins with a preamble about how the stone and the solution that we are dealing with. So this question is broken down into two parts. So the first part is about the mixture of different compounds, and the second part, well, I'll show the second part later. So if you haven't tried it yet, this is your last chance to try it before we go through. So let's just begin with a solution to the first part. So 1.1, identify X and Y. So when I am given a lot of information, such as this huge table here, I like to draw myself a little flowchart. So that will help me deduce things step by step very well. So we start off with 10 compounds. I mean, there are 12 boxes here, but only 10 of them are unique. So that's the first thing you need to realize. And then you can read the next paragraph, and it says that there are 4 substances here that you need to be concerned with, and the 4 of them come from these 10 compounds. So that's the second thing to take note of. Then 1.1 deals with substances X and Y only, and we are given that X can isomerize into Y in an acidic medium, and that Y has a plane of symmetry. So let's just note these two pieces of information down. Actually, there are 3 pieces of information. So let's start with X and Y have the same formula. And the first piece of information basically allowed us to eliminate a lot of the options already, because we know X and Y come from these 10 compounds. So you cannot have 1, 4, 7, 8, which have like different numbers of carbon atoms, so you can just eliminate those in a second. And after a closer look, you realize 5 and 9 don't have the same formula either, because they have different numbers of hydrogen and oxygen. So you can eliminate those 2. And then the second piece of information we have is that Y has a plane of symmetry. So that gives us a lot more things to work with. So from molecules that we haven't eliminated yet, although they all have the same molecular formula, you can easily find that 6 definitely does not have a plane of symmetry, because this is like a group that can just like freely rotate, and then it's in no way symmetrical. And then you can take a look at the others. Well, 10 is definitely not symmetrical. And we have 3 compound 3 here, and turns out it does have a plane of symmetry. And if you take a look at molecule 2, it doesn't have a plane of symmetry, though this part might have suggested it. But there's no way you can see the symmetry in this if you like look at it closely. So we're left with compound 3. So if you can't see its symmetry very at first glance, I think a good way to imagine this is like if you have a book and you open up the book and you have like a kind of a page in between that you can turn, that's a little flap, and if you turn it, it kind of overlaps directly onto the second page, and you can imagine this part as the spine of the book. So yeah, so this part and this part are symmetrical. So yeah, it's kind of like a star fruit, but with only 3 I don't know what the angular things are called, but yeah, maybe you get the idea, maybe not. I don't know whether that's a very good metaphor, but yeah, it's like a star fruit with 3 lobes. Yeah, probably lobes. Yep. So the 2 lobes are symmetrical. Yeah. And the plane of symmetry basically goes through this plane containing the oxygen, and it just cuts through the middle of the 2 planes, and it cuts through this methyl group. Yep. So part 1 is oh, we haven't finished it yet. So Y has a plane of symmetry, so we know Y is this compound 3. But then we need to think about how or which of these molecules can isomerize into compound 3. So our choice is either compound 2, 6, or 10. So one thing you should note is that it's very hard to break carbon-carbon single bond, and certainly not in any acidic medium. Like, yeah, sometimes it breaks, but usually there are simpler things you need to think of. So compound 2 and compound 10 don't really have like a place or a way for them to rearrange into number 3, because like you need to break so many carbon single bonds and you need to like kind of like shift the atoms around. So like it's more logical to start by thinking about how compound 6, which has many pi bonds and also the lone pair on the oxygen. So like it's better to think about how compound 6 might isomerize into compound 3, because that's a easier starting point. And then you realize that, hey, we have some things that we can spot in both 6 and 3. So you see these two methyl groups here, they are the methyl groups here, and the oxygen here, you can imagine, I mean, it is next to this methyl group, and here it is next to this methyl group. So at this point, we can be pretty sure that compound 6 can isomerize into compound 3. And yeah, I mean, it's a pretty good guess already, so you can just put that down as your answer and move on. And actually, that's what I suggest you can do in a competition. You can put a little note for yourself to come back later. But yeah, this is a very logical answer, and it is the very first question of the competition, so don't overthink it. That is the answer. But for curiosity's sake, we're just going to quickly go through the mechanism of this transformation. So it's just for fun. Don't do this in a competition. You can like quickly do it in your head, but you don't need to draw it out. I don't think this will gain you this will help you gain any marks. So it's really just for fun for you to think about and practice your mechanism drawing. So the first step in drawing mechanisms is always to label the carbon atoms. So I recommend you to label the consecutive carbon atoms with consecutive numbers. But here, I can't really do that because you have one, two. I mean, you can, and then you have to label this carbon something else. I mean, the point is, it doesn't really matter. Just do whatever that helps you to identify which carbon is which and where they end up at. So you can label 1, 3, 4, 5, blah, blah, blah. And you don't need to label the oxygen because there's only one of it. And then you can label them, the carbons in a final compound. Sometimes you can't do that very easily, but here you can. So you can just, this carbon center, number 7, is quite identifiable by being connected to an oxygen, a methyl group, and 2 other connections. So you can see that it's connected to 8, 6, and 10. So you just label those carbon atoms. And the second very identifiable carbon is number 3. So 3 is linked to 2, 1, and 4. And somehow we notice that, oh yeah, do the easy ones first. And the rest you just have to go through process of elimination. I mean, 5 and 6 can swap with 9 and 8. It doesn't really matter. They're symmetrical. And so the next step is to consider the bonds broken and formed. In this case, we notice a new bond forming between 4 and 9. And it's very easy to notice because the gap in the number is very large. Like, it's not consecutive, so you know that's a new bond. And then we also have a new bond O to number 3. So that's a new one you need to take note of. And then it's also very important to look at the conditions, because that will give you a clue about what mechanisms are reasonable under these conditions. So our condition is an acidic medium, and the question didn't say much about that other than that it's acidic. So we know it's probably not going to be too harsh or anything, because that would probably just like make the question, make it necessary for the question to put in an additional statement. So, yeah, with these few pieces of information, we can just decide on a mechanism that is likely. So, in this case, we have an acidic condition, so that can easily turn this group into a H2O leaving group, which is neutral. So, that would be a good leaving group. And also, that the HOMO of this molecule is probably placed on oxygen, for those of you who know molecular orbital theory. So that's going to be the most reactive place. So this lone pair is just going to grab an additional hydrogen to turn this into a good leaving group. And because we have a leaving group, well, the logical thing for the leaving group to do is to leave if it's a good leaving group. And after it leaves, we notice that we will form a tertiary carbocation. And not only is it tertiary, it also has an adjacent double bond next to it, which means that it will be resonance stabilized. So it's a tertiary carbon cation and carbocation, and it's conjugated, and that makes it a really good intermediate. And that's why I think SN1 is going to be likely here. So let's work with what we know. So we know SN1 is going to happen. So the first step of SN1 is leaving group. So just write whatever you think is the case down. And if it doesn't work, we'll go back and check each step. So there's no need to just like play it all out in your head. The best thing is to write something down on paper and don't cancel your working no matter what. No matter what. So if you think this is wrong, you write down something new before you cancel this, because your mentor can fight for marks for you. So you need to give them something to work on, something to work for, fight for. So yeah. Anyway, just write down the first step. See how I label my atoms here because it's quite a long chain and I don't want to miss anything out. So the second step is basically there's a carbocation here, and well, you can picture how the 4-9 bonds are going to form. It is going to form because you know it's going to form, and you know it's going to form somewhere, and you know the oxygen is going to shift. So the oxygen shifts to carbon 3, and the most logical thing to do here is to transfer the positive charge to carbon number 3 somehow, so the water can come back to it and attack it. So you can just like one way to think of this is just imagine this positive charge is delocalized over these 3 carbons, and because of that, carbon number 9 is probably going to be slightly partially positive charged, and that's why this electron-rich pi bond will just like kind of attack number 9, so that the positive charge is going to be transferred to another tertiary site. So that would be more stable. So we go from one tertiary site to another tertiary site here. So energetically, that does not cost too much. And also we form a new CC single bond. So that's going to be very favorable energetically. And then we have our water coming back. Please don't draw a hydroxide here because it is in an acidic medium, so hydroxide is not going to exist. And it comes back, and then after it comes back, it will lose one of the hydrogen, like one of its hydrogens, so the oxygen will go back to being neutral. And then after it loses the hydrogen, this pi bond basically gains a hydrogen, and it gains the hydrogen and carbon number 8 to leave a carbocation at carbon number 7, because the cation would be more stable at carbon number 7 due to more hyperconjugation than it would be at carbon number 8. And that's why the intermediate will have the positive charge here, and then the lone pair on the oxygen can kind of come back and attack here. The reason this can occur is if you count the number of atoms between the between the attacker and the attacked, you can count 1, 2, 3, 4, 5, 6. So that's a 6-membered ring. That's going to be the transition state, and that's going to be quite favorable because it doesn't have additional strains. So the transition state is going to be lower in energy, and that's why this reaction, this cyclization happens very easily. Also, because it's an intramolecular attack, it is going to happen quickly, and that will give you your final compound after you lose the additional hydrogen to restore the charge, like the neutral charge. So we can see that in the first step, from this structure to this, we gain the hydrogen, and in the last step, we lost the hydrogen. So this is hydrogen. Sorry, this is an acid catalyzed. Oh yeah, I should mention it's a hydrogen ion. Sorry. Yeah. So not the hydrogen gas. Yeah, it's the hydrogen ion, and because it is catalyzed by that. This is an isomerization because the starting and ending compounds are the same. And that's why we know nothing is going to go into it because it is yeah, it is they are isomers of each other. Of course, catalysis don't have to yield isomers, but this is just one type of catalysis. Yep. Okay, let's move on, I guess. Yeah. Anyway, you don't need to draw all that in the competition. Just don't waste your time. Also notice the symmetry. So after this step, the molecule is pretty symmetrical. Like starting from this step. So if there's symmetry in a product, there must be some kind of symmetry in the intermediates. Yeah. Okay, let's go to part 1.2. And knowing that, I forgot, is it X or Y? Yeah, X or Y. They are these. You can basically cancel them out, so you don't have to worry about them again because you can just read the question, quickly read the question, and you realize X and Y don't appear again. So yeah, just cancel those out so you have less options to deal with. So let's read this part. It's about compound Z and compound A and B. Compounds A and B, which are not here. So, yep, let's begin with compound Z. Compound Z is here, and we have more information about compound Z to elucidate it. So, when substance Z is chlorinated, a pair of peaks with intensity ratio 3:1 is observed in the mass spectrum at these two values. So there are only two peaks. That means there's only one chlorine being added, one chlorine atom being added. And the 3:1 ratio is simply the ratio of the two isotopes of chlorine, namely chlorine 35 and chlorine 37. And because you can imagine if you add like how do I explain this? I mean, like if you add two different things with different masses, then then you start with the same mass, you end up with different mass. So that's basically it. And the ratio of um the things that you try to add on that has different mass is that have different masses. It's just the ratio you get for the final weight. Yeah. It is kind of similar to the chocolate problem where you have like one poison chocolate, like sorry, a stack of poison chocolate that's like 1 gram heavier than all the other chocolate. I don't know if you have heard of that problem, but I think yeah, I saw a video of it. So yeah, it is similar to that problem, and this is basically that. So, mass spec is you just produce a radical of a substance, and it kind of breaks down, and you kind of elucidate what the original substance looks like from the other fragments, and yeah, all the ions. Okay, so there are several ways we can interpret our first findings. So we know there's only one chlorine added. So are we adding HCl to it? Because there seems to be a lot of double bonds here. So are we doing an electrophilic addition of HCl? Because that would add one chlorine. But that does not make sense because then the these two will be odd because if because like all the molar masses here are even because whenever you because carbon has like an even mass and oxygen also, and hydrogen have like odd masses, but each carbon will be connected to like only when there's nitrogen, because nitrogen is like it has an even mass but always have a valence of 3, which is odd. Then it will possibly yield an odd mass. But for oxygen, its valence is it forms two bonds. That's what I mean by that. So it forms two bonds, and carbon forms four bonds. So they both have like even masses, and they both form an even number of bonds. So there's no way you can get an even mass with oxygen, carbon, and hydrogen, like any combination of those that forms a neutral molecule. So we know that when you start with an even mass, if you add an odd mass, it's going to be odd, but the final mass here is not odd. So we know we can't have added HCl. So now we have so now we know that we added so now we know we probably replaced something rather than just add it here. Added it here because they deliberately said when substance Z is chlorinated instead of like when chlorine or whatever is added to the substance. So there's a possibility of substitution here, and just nice because chlorine forms one bond and has an odd mass, and hydrogen also forms one bond and has an odd mass. You can replace replace the hydrogen with chlorine, and you would end up with an even mass. So let's try that out. So 218 is the one is the mass after we add chlorine 35. So we're going to minus 35 here to get the um mass of the compound without the hydrogen. But we have the hydrogen to begin with because we replace the hydrogen with the chlorine. So we're going to add one back, and as expected, we get an even number. So 184. So let's see if 184 corresponds to anything here, because that will correspond to the unsubstituted structure. So you can just calculate all the um and all the masses here, because you don't have many compounds, and you can just calculate them relatively quickly because you have a very powerful calculator in the competition. But if there are too many, or if they're asking you to suggest a structure, then a good thing you can do is that you can first picture this is something called the rule of 13. So it works when you have hydrocarbon, or if you have a hydrocarbon with something that's common like oxygen, or like basically anything else, and that you are aware of the heteroatoms. So here we know that we are dealing with oxygen only, so we can see that we can hypothesize we have like 0 oxygen, 1 oxygen, 2 oxygens, and so on, and we have all the cases, and then we can just get the mass without the oxygen for each compound. So we know the total mass is 184. Then without the oxygen, the 184. If we have 0 oxygen, it would be 168 if we have 1 oxygen, and so on. So why is that useful? Because for compounds with more hydrogens than carbon, which are like most of the compounds, organic compounds, then you can use this rule of 13. It's only when you have more hydrogen than carbons that you can use it. So you are going to divide the molar mass of the compound you're interested in, the molar mass without all the heteroatoms, just like the molar mass of hydrogen and carbon only. That's like the molar mass you're dealing with. And you're going to divide it by 13, and that will give you the number of CH units. Of course, sometimes you don't get a whole number. Actually, most of the times you don't get a whole number because the molecule is not made up purely of the CH units. So CH units is when because each CH unit weighs 13 like it has a mass of 13. So if you divide the entire mass by 13, you're going to get how many CH units there are. And because you have a remainder term here, just use like the fraction function on your calculator, you get a remainder, and the remainder is going to tell you how many extra hydrogens you have other than the ones considered in the CH units. So that's because you don't have a complete CH unit, and you don't have like, I mean, if the remainder is 12, sure, you can have like more carbons than hydrogen. You can have one more carbon than you do hydrogen. So this 12 here could mean a carbon or 12 hydrogens. But yeah, here we see all the compounds definitely have more hydrogens than carbons. So we're not going to care about the C13H12 case. So the number of CH units, let's use the first one as an example. So the first one is the number of CH units. So we know we have C14H14. However, we have 2 additional units of mass, and that will give us 2 additional hydrogens, and that gives us 14 plus 2 equals to 16. So our formula will be C14H16, and we look back at the number of oxygens we have none. So that's O0. So that's C14H16, and we can check our table here. Is it present? Yeah, it is present. So it's number 7. So number 7 is probably our answer, but we're going to be very careful and check whether that is the case. So we're just going to write this down first, because if it's correct, you earn the mark. Like, you don't really need to justify it if it's correct. And then we move on to our second clue, which is that Z comes from A, and A has 2 perpendicular planes of symmetry. And we notice that Z already looks kind of symmetrical if you draw like a plane of symmetry here. And the only thing preventing it from being symmetrical are the substituents on the rings. So if we remove those rings, then yeah, Z becomes substance A. So one plane of symmetry is here. You can imagine it cutting down perpendicularly into the screen. And the second plane of symmetry is here in a plane of the like aromatic part. So we're also told that when heated, A isomerizes into aromatic compound B. I mean, Z is kind of aromatic by the core of it. A is also aromatic, but like there's an even more well-known aromatic, which is B. I think this is naphthalene, and yeah, I mean, it's like there aren't many possibilities. You can just like imagine, and then it looks like this. Another thing is you can count the double bond equivalent of A, which is 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5, 6, 7. And hold up. 1, 2, 3, 4, 5, 6, 7. I suppose it's supposed to be 6. 1, 2, 3, 4, 5, 6, 7. That might be where I think I'm counting wrong. Oh wait, sorry. Yeah. Yeah, it is correct. So 7. So 7 is just one ring with 4 degrees of unsaturation, which is like a benzene ring plus 3 additional degrees of unsaturation. And to maintain aromaticity, you can just add one more ring. I'm sorry, yes, in my brain I was kind of like hinted at myself. I need like 8 degrees of unsaturation to get 2 benzene rings and then piece them together. But I overcounted because this double bond is kind of shared in between them. I know it's delocalized, but in the structure it is. So yeah, confusions do happen. The thing is, don't overthink in the exam. Yeah. Okay. So yeah, those are A and B. You get 4 points. But I mean, they scale the points, so like it doesn't really translate to 4 points in your overall marks. Yeah, you get 4 points. Yay. Okay. So let's go on to the next part. So we know that 7 is out of the picture as well. We're not going to see it again in this question because as a smart person you are, you have read through the question, you know what the question is talking about, and yeah, and to save yourself from the trouble by crossing them out. Okay, so we're left with, well, still quite many molecules. Yeah, so let's just read on. So this part talks about W, and the first piece of information you have is when W was added to an aqueous solution of iron 3 plus ions, a characteristic color change was observed. So my guess is this color change is from yellow, like the your rust color, to kind of like green to Fe2 plus. So that's, I mean, Fe3 plus doesn't do much other than get reduced, and it's not like Fe3 plus is not very oxidizing. So yeah, that the thing you have is probably reducing. So you shouldn't have like something in its top oxidation state, because for example, if your one part of your molecule is like already fully oxidized, then it can't really react with the Fe3 plus again. Of course, another part of your molecule can react, but yeah, but you can just check both parts out. Anyway, that will eliminate these three options, because here we only have CC double bond, which doesn't do much here in terms of oxidization. Sorry, not oxidization, oxidation, yeah, oxidation. And unless you have like a really strong reagent like KMNO4 and you just like whack the thing. But that's not what's happening here. You have like a weak oxidizing reagent, so yeah, not gonna happen. And you have two ketones here, not gonna happen, because they are already quite like top oxidation state, the carbon here, and you're not going to do anything to the CC single bonds because it's not that reactive. Yeah, so gonna eliminate those three. Let's take a look at the other few. So here we have like ketone. This part is definitely not gonna get oxidized. And then we have other groups. So let's just move on to the next clue, because we don't know what's happening yet. So mass spec reveal the intensity ratio of the M plus and M plus 1 plus is 9 to 1. I mean, I guess this year has a lot of mass spec questions because it's one of the special topics. I'm not very sure. But yeah. So M plus 1, oh, they told you here it's due to the 13C, and the M plus is the 12C. So there is also they also gave you the natural isotopic abundance of C12, and yeah, so you can just find the number of carbons from the mass data. So the M plus gives you the number of 12C, and the M plus 1 intensity, M plus 1 plus intensity gives you sorry, not the intensity, yeah, what I meant to say is that for the molecule with mass of n plus, you are it is basically made up of n number of carbon 12, and for the mass that is 1 unit higher, you have n minus 1 number of carbon 12 and 1 carbon 13. So you just take out one of the carbon 12 and you replace it with carbon 13. It doesn't matter which carbon, because you have the entire like unfragmented ion here. So you have the entire mass, I mean minus 1 electron, but the electron is not going to count because it's so light. So yeah. So you don't know which carbon you can take out. So it basically includes all the possibilities. So yeah, it's just take out carbon 12, replace it by carbon 13. And then the intensity ratio is basically the probability ratio of these two species existing. So having like all 12 carbons being um no, sorry, not all 12 carbons, like all the carbons being carbon 12, the probability is the number of the probability of each carbon being carbon 12, which is 0.989. So that's quite a high number, large number, to the power of n, because you have n carbons. So you are going to have 12C, 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 and so on. Then for the 12C, n minus 1 12C and 1 13C combination, you the probability is 0.989 to the power of n minus 1. So you're going to have 12C, 12C, 12C repeated for n minus 1 time. And you're going to times it by the probability of the last carbon being 0.011. And then you can choose any of these n carbons to be the 13C carbon. So you're going to time this by n, and by dividing this ratio, you will get a ratio of n plus to n plus 1 plus, which is 9:1, which is 9. So if you um do some rearrangement, or you just ask your calculator to solve it for you, you'll get n equals to 10. So out of these three, only number 5 is n equals to 10. So let's double check whether that makes sense. Um, you have uh yeah, you have W here, and oh, actually, they just asked you to show your calculation, so this must be right. Like, there's a reason there are 10 columns there, and I mean, yeah, that should be it. Actually, I realized that the role of iron here is not to oxidize, but rather, um, like, there's a famous reaction between like iron 3 plus and phenols, and I just realized that we have like three phenols here, so it's not very, sorry, we have two phenols here, so it's not very useful to distinguish between 1 and 5. So the rule is not to oxidize here, but after you kind of like deprotonate the phenol, like the thing kind of just coordinates to the iron, and actually the color change is not from yellow to green. I apologize for my earlier mistake. It is from yellow to a very intense purple. I almost forgot about this reaction, and I was thinking, where can W even get like oxidized? Like, what's the difference between it and the other molecules that enable it to be oxidized? But the reaction is not an oxidization at all. Not an oxidization. I said oxidization again. It's not an oxidation at all, but rather, it forms a complex with the ion. So, and that's why they say it's characteristic. Okay, now I now I get it. I am sorry, guys. Um, yeah. Let me see if I can cross this out. That is my mistake. Let me cross that out and write complex. Feel free to skip ahead this part, but I am very determined to correct my mistake. So it's a complex formation. Okay. Yeah, not gonna finish the word. Good enough, I guess. My apologies. My apologies. It is a complex formation reaction, and it will be purple, and it's good to know this reaction. I guess I haven't done this in too long, and I forgot about it, and I kind of confused myself, and therefore I paused the video to just like check what the heck is happening here. So yeah, purple. Anyway, okay, moving on. um, how do I clear this? Let me check. Erase or ink. Okay, going back to the laser pointer. Moving on. Let's yeah, sanity check completed. Not right. Okay, part two. Hopefully my sanity returns during this part and I can do this properly. So let's go to 1.4. Identify metal Q in these compounds. So 1.4. Okay, let's read this huge chunk first. Uh it is a compound, blah blah blah, dissolved, adjust the pH, added NaF. I guess added the NaF, it's the very important part. Anyway, they gave you a reaction flow chart. They didn't even like bother putting this in, so probably not important. And NaF added, and you get this uh compound precipitate thingy with waters of crystallization. So yeah, before dealing with like all the numbers, which might overwhelm you, just do what you can with the qualitative information first. So we were told that she dissolved it in dilute nitric acid. So what is the role of the acid? It's probably just dissolution. There's like no indication of other reactions, like oxidation, oxidation. Yeah, it should be oxidation. I don't know what I was doing while typing this slide. So it should be oxidation. My apologies again. Yeah, and there's no like descriptions of like bubbling, color changes, or whatever. So yeah, probably just dissolution. And second thing is, what is the role of NAF? Um, I mean, there's not much you can do when you just like add a salt to another presumably ionic compound, other than like precipitation, like partner swapping. So you can probably say that the cation in C, so that's those precipitate, um, it likes the fluoride so much that it kind of swaps out its previous anion partner, which we don't know what it is yet, but it swaps it out to just like hold on to the fluoride and kind of crash out. And so yeah, that's the role of NAF. And where does the metal Q come from? Like, of course, it is present in the precipitate. Because when I said C reacted with in excess of NaF to yield D, you have sodium and metal Q and like definitely fluorine as well. So the Q can only come from C, and the C definitely comes from the stone. So it's kind of like a continuous thing, so you can't just like stop somewhere and make a metal just pop up. So yeah, metal Q comes from C. And that's an important thing to know because now you know more about C. You know it contains metal Q. So after we have like gleaned all the possible qualitative information, let's go with quantitative information. So time to work with the numbers. I don't like dealing with like a lot of equations, so like I usually work with tables. So like imagine we have 100 grams of precipitate to start with, and then you can split it into the anhydrous part and the waters of crystallization. So there's 39.16 percent water by mass. So that translates to 39.16 grams per 100 grams, and the rest is basically the anhydrous precipitate. And then we know the mass, we know the molar mass of each of these. So water is 18.016 and anhydrous PPT we don't know. We're just going to put M here as a variable. So the amount is just the mass divided by the number of the amount is the number of moles, so it's the mass divided by the molar mass, and that gives you these two expressions. So we know from this formula here, the ratio of water to C is X is to 1. So we're going to equate that. So this to this is 1 to x. So you bring the x over, so you get 60.84 divided by m times x equals to this thing on the right hand side, and rearranging everything, we get m equals to 27.99 times x. I usually find multiplications easier to work with than divisions because that will allow me to squeeze everything into a single line, so that's what I usually do. Just change everything to multiplication. So our strategy here will be to sub in different values of x, find the corresponding values of m, and record the value of the molar mass of precipitate C without fluorines. So that sounds complicated. Let's just draw another table. Well, the more you do this, the easier it will be, and the faster you can do this as well. So x equals to 1, 2, 3, and so on. And I didn't include the rest because, well, I did this on paper and I know it's going to stop at 3, but be prepared to draw a very large table to record down all your answers. Of course, waters, like the number of the waters of crystallization doesn't have to be a whole number. Like there is something with 5.5 waters of crystallization, I think, and those things happen, but it's fine. We're just going to try all the whole numbers first. If that doesn't work, we expand, like we go back and revisit our assumption and see whether that's correct. So we go with the whole numbers first because that's the easiest thing to do. And then we can suppose that C contains like 1 fluorine or 2 fluorine, 3 fluorine, and so on. Like it might be a very long list. It does not matter at this stage. But we know it's not going to be too many fluorines because we added excess NAF afterwards and more fluorine went in. So it can't have like too many like things. So yeah. So let's calculate for the case of x equals to 1. So small m will be 27.99. And because we have 1 fluorine here, we're going to minus 19.00 from 27.99, and that will give you 9, which is quite close to beryllium's molar mass, but that's not going to be the case because what is BF? Like, it does not really make sense. So we're going to go for the chemically sound answer instead of like the mathematically closest one, because these things are measured with experiments, and any experiment is associated with like a certain like error that you just can't like eliminate even if you're very careful or whatnot. And you notice here that the numbers are only given to 4 SF, and the last SF can actually be like, so you can have like anything from 39.16 4 to 39.155. So like that's a huge range, and that's going to affect your last decimal place here, or even like the decimal places before that if you have like a multi-step calculation, or if you rounded off your values like prematurely, or even the exam setter rounded their values prematurely before the final calculation. So you're not going to trust the last few decimal places. You're going to trust your chemical intuition, and that's the most important thing. So we're going to go with 2. For here, I stopped like minusing off the molar mass of fluorine because like it's going to go negative, and there's no need to do that. So you notice that when we go from x equals to 1, 1f, x equals to 2, 2f, like if you go along the diagonal, you're just going to get multiples of 9. So that's something that will allow you to fill out the table very easily. So x equals to 2, and small m equals to 27.99 times 2, and then you are going to minus 1 fluorine molar mass, and so on here. And yeah, so you get the idea. And you hit nothing. So it's always sensible to go kind of like diagonally along the table because like that's where you're most likely to hit. And finally, at x equals to 3 and the number of fluorine equals to 3, you get 27.00, which is aluminium. And yeah, maybe metal Q is going to be aluminium, but you're going to make sure it is before you just like kind of like move on, because like what we did in the previous part, this metal Q actually ties to the next few parts. So if you don't get this part, you're not going to get the next few parts, because this is elucidation. This is not where you can get like error carry forward, because if it doesn't make sense, it doesn't make sense. And all the reactions are not going to make sense, and to that, and you might mislead yourself into something else and wasting your time trying to check all your assumptions in the later part when it's the first part that you have made an error in. So it's always good to double check when it's the first part of an inorganic elucidation problem. So yeah, metal Q might be aluminium, and we're going to see whether that makes sense. See, we have aluminium and we have three fluorines attached to it, so that gives us AlF3, which makes sense because you know aluminium forms three bonds, and you know it likes hydrogen. So AlF3 makes sense. Now, to really, really check your sanity, you are going to think about the next part, whether the next part makes sense. So let's just put this down as a preliminary answer first. 3 waters of crystallization, 3 fluorine. And then we move on to the next part. And if this next part doesn't work out, we go back to visit this part. So because we're still within part 1.4, so we're good. Just don't move too far down the line. So next piece of information. Anhydrous C reacts with an excess NAF to yield compound D, which contains some sodium and 12.85% of metal Q by mass. So if you find something that satisfies both, then you know, well, you're probably on the right track. So yeah, we're going to do the same thing again. After a while, you notice that this is quite systematic, and after a while, it just gets faster and faster. So don't worry if you can't like do it really quickly now. You're going to do it like much more quickly in the future. So don't worry about that. Imagine we have 100 grams of D. Now we have a guess for metal Q already. It's aluminium. And we have sodium, and of course we have fluorine because we already had some fluorine in C, and more fluorine basically went in because um even in the scheme they gave us, it's C, NAF, 2D. Like there's nothing else produced. So the only logical thing is to guess that all the NAF went into C. So we do the same thing, mass, so 100 grams, 12.85% of 100 grams is 12.85 grams, and so on. And the molar mass, you can get the following from the periodic table you are provided with. The amount, which is the mass divided by the molar mass, and you're gonna the amount in moles. And the next thing which we didn't do just now is the ratio, because just now the ratio was apparent. It's 1:x. But here you take the bigger numbers, you divide it by the smaller numbers. Like sometimes you don't get a whole number, just scale the whole thing up. So the ratio is very nicely 1:3:6. Now sanity check time. Does this make sense? Well, just now we had C is ElF3, and then NAF, we can just have like 3 additional fluorine and 3 additional sodium, and that give us 3 of NAF. So we know indeed all of the NAF went inside C. And so we're pretty sure that aluminium is our metal Q and compound D is AlNa3F6. So imagine you didn't have time to do this. You would have already gotten the mark for the previous part by writing this down. So just write your guesses down, even if you're not sure about it. But always double check before you move on. Yeah, let's move on to 1.5 since now we're reasonably sure of our answer here. So several pieces of information. The stone was found in a coal deposit. I think it's deposit. Yeah. Anyway, coal means carbon. Some form of carbon is present, and the stone contains an anion of a highly symmetrical acid F. So when you're hit with carbon and you're hit with acid, you're going to think about carboxylic acid. So F is going to be a carboxylic acid, and you know it's going to be highly symmetrical. So F then reacts with P2O5, which is an oxidizing reagent, and a strong one at that. And you're just going to note down this rule really quickly so you don't have to refer back to the text while doing your question afterwards. And then you have a binary compound G, so write down binary, and and you can just like write down the rotational axis. So E is 6-fold rotation, and G is 3-fold. So somewhere in between, the rotation got destroyed. Yeah. And the sixfold, like if it's like, let's say, A B A B A B A B, like repeated 6 times. After that, it's threefold. You know that like A B A B probably got grouped together, so the six got reduced to three. So it might have become um like AABB or something like that. So it's going to be like a systematic destruction of the rotational axis rather than like you just like remove something in the middle, because like if you do that, then more axes are going to be destroyed. Stop just now. We're just going to move on. As we discussed, it's all qualitative information. And we know G is probably going to contain oxygen because it has been oxidized before, and the carbon is not just going to fly away, so it should contain at least carbon and oxygen. So let's just begin with that assumption first. And the next step is to work with the quantitative information. So again, imagine we have 100 grams of G, and then we draw a table. We have our carbon and we have our oxygen. So this is just our starting assumption. We only have carbon and oxygen. So we have the mass from the percentage. Oh, actually, that's not our starting assumption, because remember, G is binary. So we know that it only contains carbon and oxygen. Oh, that makes our life so much easier. Yeah, I even wrote it down just now. I just kind of forgot when going through the video, like going through the slides. Yeah. I wrote it down while making the slides, but anyhow, um, yeah. So, we have carbon and oxygen. Yeah, life is much simpler. So, we're going to divide the mass by the molar mass, get the amount, the story, and then we get the ratio. So now we have the empirical formula of G, and at this point, you might wonder what n is, because like we have n repeating units. But then we notice that G has a threefold rotational axis, which means it doesn't have a sixfold rotational axis, because the question phrased it this way. And so we know that n must be 3, because if it's anything else, then it's not going to divide. Like the entire formula is not going to divide by 3 um properly, and because of that, it's not going to work out, because if you have something like 6, then you will have a sixfold rotational axis, because you already have a threefold. Then unless you kind of like mess up the middle a little bit so it's not symmetrical, um then you can't then you must have a sixfold rotational axis, and there's no reason to believe that the middle is kind of like unsymmetrical, because if it is, then threefold would disappear as well. So n must be 3. If it's any other number, then the threefold rotational axis wouldn't exist as well. So yeah, n is probably 3. And so we can fill in our preliminary guess here. We're going to check whether it's correct. And because it's unlikely for the carbon to fly off, you know that E and G must contain the same number of carbons. So E might contain some oxygens. It must contain some hydrogens, because here we're given E contains 11.18% of hydrogen by mass. Oxygen not sure, but hydrogen and carbons are definitely there. And you notice that 11 point something percent of hydrogen is quite high as a weight percentage, because like hydrogen is quite light as an element. So we're going to try without oxygen first, instead of starting with the highest possible number of oxygen, and then we're going to slowly increase the number of oxygen if needed. So suppose E has no oxygen, you have your carbon, you have your hydrogen, do the usual thing, mass, so 11.18, 100 minus 11.18 is 88.82, and then molar mass, divide, get the amount, and just nice, you have a ratio. And such nice ratios are rarely coincidental. So you're going to think that E is C2H36, so the number of carbons will stay the same. Same for E and G, and that can rearrange into something with a six-fold rotational symmetry. So that is a really good step forward because right now everything has been verified. Now we just need to make sure that we can explain what is happening. So E is this, and you notice that you have six carbons, then you have six methyl groups. It's a really nice arrangement, and that reminds you a lot of a benzene ring with six methyl substituents. And so you write down this set of answer, and for G, the benzene ring must be there because like you can't really do anything to it. And then to maintain the symmetry, you put the oxygen here and here. And for F, because you know it's a carboxylic acid, and the position of carbon can't really change, they must be placed at where the methyl groups were, and the number of carbons stay there, like stay the same. So then you want to make sense of your answer, whether your answer is reasonable. Because how come F just goes to G and how come E goes to F? Well, the first thing to notice is that E has a lot of benzylic positions, and benzylic positions are very activated, and therefore you can do oxidation on it, especially when you have such a strong oxidizing agent like KMnO4, and therefore it will turn each of the methyl carbons into its highest oxidization state, and then you will have six carboxylic acids. That makes sense. Now, how does F turn into G? If you compare the formula of F with G's formula, you will notice that G is basically just missing some water molecules from F. And because P2O5, if you remember, for industrial processes, sometimes we use strong acids to dehydrate stuff. Like when we use sulfuric acid to dehydrate I think alcohols, and that will give you alkenes industrially. So that's something you can do because acids just like take up water really rapidly and they're really greedy and they dehydrate stuff as well as like they can, because here P2O5 also oxidizes things, and also you can have like something like some like phosphorus containing strong acids like phosphoric acids, and you know that this P2O5 is an oxidizing reagent, so like it can be both oxidizing and dehydrating. Actually, in this case, what does it really do? Let me check. Actually, in this case, no oxidation happened because the carbon ox- oxidation state actually remain the same. So actually, my initial assumption is wrong again. So I'm going to cross that out. Bad mistake. So it's not oxidized, rather it's dehydrate. I think I would have just missed that in the competition. Um, yeah, I would have just missed that in the competitions, but well, it's my fault for not checking the slides after I make them. But anyway, I guess it really helps for me to like think out loud, and then I discover a lot of mistakes I make. Yeah, so it's to dehydrate. You remove let's see. Yeah, you remove a water molecule like for every group like this. Yep. In case this doesn't really come out clearly. Let me go back to the Facebook water. So this OH and this H basically fly away, and the two things condense. And that's why your symmetry is destroyed. I mean, three full symmetry remains. So it's here, here, and here. Used to be like here, 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 and here. Yep. So it's basically this one that got destroyed. Yeah. I really apologize for that. It's a dehydration, yeah, as written here, rather than oxidization. Oxidization, I don't know why I keep saying that. Rather than oxidation as suggested here. It's not an oxidation. It is a dehydration. Anyway, my apologies. Let's move on to the, I think, last part of the question. So this is a fun one. So she basically heated a stone, and I don't know if you'd remember by this point in the question, but it was mentioned that a stone was stoichiometric. So like it has a fixed chemical formula. That's quite important here. So it's actually a compound, it's not a mixture. So it's unlike the solution that we investigated in part one. So a 10-gram sample, well, this time they gave you the mass, quite nice, began to lose mass at approximately 100 degrees, and that's because it loses water. So when you see mass loss at 100 degrees, think about water. And then so that a second drop in mass observed at 400 degrees, and that's decomposition because you have a sharp temperature, and that suggests a chemical reaction happening. And this is the information we already have. We know the stone contains the anion of F. So F is the carboxylic acid we drew just now, and we have aluminium 3. We have also waters of crystallization. And just using this information and the information below, we already can write out the formula of the stone. So its charge balance gives, because Al is 3 plus and just now the anion of F is 6 minus, there's no reason for it to lose some hydrogens but not others. So we assume all hydrogens have been lost. So it's Al2 COO6. I just wrote it like that so it's easier to read. And easier to see the charge directly, and N waters of crystallization. So again, we do the mass thingy. So the mass of the anhydrous stone is 5.75 because after it loses water, it's flat, and the water is basically the mass that flew away. The molar mass of the anhydrous stone, you can just calculate it from here, like the molecular formula here, and real mass of water, and then total mass divided by molar mass, you get the amount, and then you have the ratio. And N equals 16. That is quite high, but, well, to be expected, given that this stone seems really special. So, knowing that the stone has this formula, we're going to verify whether H is the aluminium oxide, because from this formula, we can easily see after water flies away, the most logical thing to do is for the CO2 to fly away. So it gets, well, decarboxylated in a sense. So H is probably the oxide because it's 400 degrees. That's insanely high. And so the only thing that's going to be stable there is probably the oxide. So you can do this as an exercise without looking at this, or you can just see the anhydrous stone has this mass, 5.75, and the final mass of the oxide, well, the allegedly oxide substance is 1.5 grams. So we're going to divide it by the molar mass and find the amount and find the ratio. So we see, as expected, there are 2 aluminium here and 2 aluminium here, and the ratio is 1:1. So indeed, H is the oxide. And yeah, that's basically it. Remember to write down the answer after you have done so many things, and don't be like me and forget to write the answer, which I just realized. Um, yeah, so, well, thank you. Um, I will probably make the next video in September. And I took a brief look at it. It's about kinetics. So I'm quite excited for that because I haven't done a physical chemistry video yet, and actually that's my strong suit, and I hope I can, well, explain that better than I do the organics, but I hope I did this one well. I mean, I really apologize for all the mistakes made. Yeah, sometimes it does take saying things out loud to realize the mistakes I made, even though like I check the slides. But yeah, anyway, I hope you enjoyed this video, and I will see you in the next one. So bye, and I really missed you guys. I mean, that sounds cheesy, but yeah, I really missed doing this. Um, during my break. The break was kind of long, but I did a bunch of fun stuff, and I really hope that I can share these fun stuff with you guys someday. Anyway, um, yeah, bye.